Composite hadrons, mesons, and baryons. Composite particles composed of quarks glued together by a sea of gluons are called hadrons. Hadrons, shown under the green here, have physical size around 10 to the minus 15 meters and are not point-like. Hadrons composed of two quarks, one matter quark and one antimatter antiquark, are called mesons and are bosons. All mesons are unstable, live less than a microsecond, and decay by the weak interaction. The only meson we will cover, and only a little, later in the course is the pion. Before the 1970s, the muon, a lepton, not a hadron, was called the mu meson, but it no longer is. Hadrons composed of three quarks are called baryons and are fermions. This includes the proton and the neutron. In recent years, the Large Hadron Collider, the LHC, has had a few detections of transient tetraquarks, 4-quark composites, and pentaquarks, 5-quark composites, but this evidence is inconclusive. You might have heard of Neutron Stars, where the compact star, less than 10 kilometers in diameter, consists almost completely of neutrons, closely packed at the high density of atomic nuclei. Collapse is forestalled by the neutron degeneracy pressure due to the Pauli exclusion principle, as neutrons are fermions. Astrophysicists have posited, but not yet detected, hypothetical quark stars composed of quark matter at higher density than a neutron star or nuclei, but not as dense as a black hole. If hypothetical quark matter were to contain strange quarks, S, it is called strange matter, and such a star would be called a strange star. Strange matter is a different concept than exotic matter, which you might see in some articles. Quark matter and strange matter have not been detected at this point. Baryons are composite particles composed of three quarks, and antibaryons are composed of three antiquarks. Baryons have mass and travel at less than the speed of light. Baryons have electrical charge of -1, 0, +1, or +2, the possible combinations of three quarks of charge +2/3 or -1/3. Baryons have spin values of 1/2 or 3/2 in their lowest energy states, the possible combinations of three spin 1/2 quarks. And so all baryons are fermions and obey the Pauli exclusion principle. The proton consists of two up quarks and one down quark in the lowest energy internal angular momentum configuration, spin 1/2. So up, up, down, spin 1/2. Electrical charge is +1. It's +2/3, +2/3, -1/3. So +1. The antiproton, P bar, is up bar, down bar. The proton is the lowest mass baryon, 938 million electron volts, and the only baryon that is stable in isolation. It is known to live at least 19 orders of magnitude longer than the age of the universe. I believe that nearly all the protons of hydrogen atoms and hydrogen molecules, whose clouds collapse to form a star, have been in existence since the second after the Big Bang, more than 13 billion years ago. Here is a stylized representation of a proton. We see two up quarks and one down quark, represented as blue, red, and green colored spheres, confined within the gray sphere. The quarks are attracted to one another via the strong nuclear force, also called the color force, having nothing to do with colors that our eyes see. The color force is mediated by gluons, which are represented by the wavy lines. Although the graphic shows 3 wavy lines, actually there's a sea of gluons throughout the composite hadron particle. Gluons glue the quarks together as the hadron. Gluons are bosons and like to bunch together. The gluons keep the 3 quarks permanently confined together within the proton or any baryon. The quarks move about within the proton and do not collapse together to a point. There's more to know about the color force and quark color charge that I'll provide late in the course as supplementary material. The strong nuclear force is attractive. The only repulsion between the quarks is electrical when they have the same electrical charge. 2 quarks can occupy the same position in space briefly, but the Heisenberg uncertainty principle limits the spatial and momentum probability distributions to the size of the proton. The 2 up quarks can occupy the same spatial quantum state when they have opposite spins per the Pauli exclusion principle. The proton has total internal angular momentum of 1/2 h bar, which is spin 1/2, viewing the proton externally as a particle. I think of the 2 up quarks as having opposite spins, but reality is much more complicated. In addition to the 3 quarks' intrinsic spin angular momenta, their relative motion involves orbital angular momentum. Each gluon in the sea of gluons is spin 1, and gluon motion also involves orbital angular momentum. This is an extremely complicated quantum mechanical system governed by quantum chromodynamics. Exactly how and why the proton has net spin 1/2 is an important unsolved problem in theoretical physics called the proton spin crisis. There is another baryon that is up, up, down, but spin 3/2, as if the 3 quark spins are aligned. This is a delta plus particle, 30% higher mass than the proton. Its lifetime is less than 10 to the minus 23 seconds. The rest mass of 2 up quarks and 1 down quark is 9.1 million electron volts. The mass of the proton is 938 million electron volts, 100 times the quark masses. How does the proton get this mass? Inside the proton, the quarks are strongly attracted to one another and are constantly moving relative to one another at speeds that can be a fraction of the speed of light. They are relativistic and their total energy is higher than their rest mass energy. But mostly the energy of the sea of gluons and also virtual quark-antiquark pairs called C-quarks surrounding the three real valence quarks gives the proton its mass, which, to us, seems merely the proton's rest mass energy. All hadrons have higher masses than their constituent quarks' masses. Here is an artist's impression of the quarks, real and virtual, and gluons inside the proton. Hadrons are extremely complicated internally, but appear simple externally. The neutron consists of one up quark and two down quarks in the lowest energy internal angular momentum configuration, spin 1/2. Electrical charge is 0. It's plus 2/3, minus 1/3, minus 1/3, which is 0. The anti-neutron, N bar, is U bar D bar D bar. The neutron is the second lowest mass baryon at 940 million electron volts, slightly more than the proton. An isolated free neutron is not stable. Its lifetime is about 15 minutes. However, nuclei consisting of protons and neutrons can be stable. There are neutrons within deuterium atoms and helium atoms that have existed continuously since the first minutes after the Big Bang, more than 13 billion years ago. Here is a stylized representation of a neutron. There are many other more massive baryons. All are unstable, with lifetimes less than a billionth of a second. All quark flavors except for top have been found in various baryons. We will not discuss these other baryons. Conservation of baryon number. Baryon number is 1/3 the number of matter quarks minus the number of antimatter antiquarks. Baryon number is conserved in every interaction since the first second after the Big Bang, as far as physicists can tell. The net of quarks minus antiquarks is conserved in every interaction. Quark-antiquark pairs are readily produced in particle accelerators. These conserve baryon number. The only single quarks ever produced were heavy top quarks that decayed within 10 to the minus 24 seconds. Neutron decay. The lifetime of a free neutron, not in a nucleus, is about 15 minutes. Here is the normal decay for a neutron. An electrically neutral neutron decays via the weak interaction to a positively charged proton, a negatively charged electron, and an electrically neutral electron antineutrino. Electrical charge is conserved. It is 0 on both sides. Baryon number is conserved. It is 1 on each side. Lepton number is conserved. It is 0 on each side. 0, 0, 1, minus 1. Electron number is conserved. It is 0 on each side. This electron is emitted with high velocity, high kinetic energy, and it is called a beta particle, or a beta minus, or beta radiation. This decay is called beta decay, or beta minus decay, or beta emission. Here is the Feynman diagram for the free neutron's beta decay. The first vertex is in common for all three quarks of the neutron. We start with a neutron, up, down, down. At the first vertex, one down quark of the neutron is transmuted to an up quark of what is now a proton, up, up, down, and a virtual W- boson. The first decay vertex conserves electrical charge 0, baryon number 1, lepton number 0, and the lepton family numbers. Then at the second vertex, the W- boson decays into two particles via the weak interaction, electrically negatively charged matter electron and an electrically neutral antimatter electron antineutrino. Antimatter particles are given an arrow direction pointing backward in time. This second vertex conserves electrical charge -1, baryon number 0, lepton number 0, and the lepton family numbers. A small natural neutron background flux of free neutrons exists on Earth caused by cosmic rays and also certain radioactive elements in Earth's crust. Prodigious amounts of free neutrons exist inside nuclear fission reactors and atomic bomb fission explosions. The lifetime of the free neutron does not impact these cases. Unstable atomic nuclei. Most atomic nuclei in daily life are stable, and the neutrons within the nuclei are stable. However, some isotopes of unstable nuclei have excess neutrons that will beta minus decay with a lifetime that depends upon the isotope, from under a second to more than the age of the universe. The image is a representation of nuclear beta minus decay. So, for some purposes, it's shown merely as a high energy beta minus particle being ejected, but what's actually happening is a neutron turned into a proton ejected a high energy electron, but also ejected an electron antineutrino. You may have heard of radiocarbon dating of fossil plants and animals that have died in the last 50,000 years. On Earth, about 1 part per trillion of the carbon atoms in living plants and animals is unstable neutron-rich carbon-14, with 8 neutrons versus the 6 neutrons of ordinary stable carbon-12. The carbon-14 nucleus will beta minus decay, with a lifetime around 8,000 years, to produce a stable nitrogen-14 nucleus. This is also part of the natural background radiation that we experience throughout our lives. Nuclear fusion in the Sun. The inner core of the Sun, and any star, is dense, high pressure, and high temperature. Our Sun fuses hydrogen nuclei, protons, into helium nuclei, 2 protons and 2 neutrons, in a 3-step process called the proton-proton chain, or PP chain. The first step is to transform two colliding protons into a proton and a neutron that fuse as a deuterium nucleus and release energy. Here's the reaction via the weak interaction. The deuterium nucleus is one proton and one neutron. So two protons collide at high temperature, density, and pressure, and the end product is a deuterium nucleus, a positron, and an electron neutrino. Here is the Feynman diagram for the beta plus decay of the proton into a neutron, positron, beta plus, and electron, neutrino. So here we have a proton, an up, up, down. The beta plus decay of the proton does not occur for an isolated proton, which is stable and has less mass than the neutron. So this beta decay that we're showing here, it occurs during a high energy collision with another proton in the core of the Sun. Beta plus decay can also occur in an unstable nucleus that is neutron poor. I think you can follow this Feynman diagram on your own and verify the conserved quantities. After this beta decay, the emitted positron will annihilate with a free electron and emit two gamma rays, which add to the thermal energy of the Sun's core. The electron neutrino flies through all the layers of the Sun without any interaction and flies off into space. 8 minutes later, some of the electron neutrinos hit the Earth and pass through it with almost no interaction. At the temperature, pressure, and density at the core of our Sun, a proton collides with other protons 1 trillion times per second for 7 to 9 billion years on average before it successfully fuses with another proton to become deuterium. However, there are so many protons in the Sun's core that 2 by 10 to the 38 deuterium nuclei are created every second. This gives the Sun the energy that we see as light and heat. This slow rate of fusion per proton is fortunate for us, as the Sun has been shining for the 4.5 billion year life of the Earth and will continue shining for another 5 billion years. Stars with more mass than the Sun burn more rapidly, up to 1 million times faster. And so many of those higher, more massive stars burned out long ago. 1 second after the deuterium nucleus is created at the core of the Sun, it fuses with another proton via the residual strong nuclear force, not the weak interaction, to become a helium-3 nucleus and release more energy. 400 years later, the helium-3 nucleus is finally converted to stable helium-4, again releasing more energy. Mesons. Composite particles composed of 2 quarks, one matter quark and one antimatter antiquark, are called mesons. Mesons have baryon number of 0. Mesons have spin values of 0 or 1 and therefore are bosons and like to bunch together. There is no meson number conservation. Mesons, like baryons, have integral values of electrical charge. Though quarks have fractional values of electrical charge, all composite particles made of quarks have integral values of electrical charge. All mesons are unstable and short-lived. The lowest mass mesons are the pions, sometimes called pi mesons. The two charged pions, pi plus and pi minus, have mass of 140 million electron volts and almost the longest lifetime of all mesons at 26 nanoseconds. The pi plus is an up quark and an anti-down quark, and its charge is +1. The pi minus is an anti-up and a down. Its charge is -1. These two pi mesons have spin 0. The pi plus and pi minus are antiparticles to one another. And here's a representation of the pi plus. The charged pions decay to muons or antimuons via the weak interaction. Here we see the pi plus decaying to a mu plus, which is an antimuon, and a muon neutrino. Here we see a pi minus decaying to a muon and a mu antineutrino. Here is a Feynman diagram for the pi plus decay. Nuclei and the residual strong force. The word nucleons means protons and or neutrons. Neutrons are composite particles, hadrons, not elementary, and are not point-like. They occupy a volume of space and are said to have a radius of about 0.8 femtometers, 0.8 by 10 to the minus 15 meters. But they do not have a definite hard spherical surface. Nucleons can overlap in space to some extent. Protons anywhere in a nucleus are electrically repelled by one another, as they all have the same positive electrical charge. Like charges repel, and the Coulomb force is long range. The protons want to fly apart. However, when a proton and a neutron have parallel spins, they are strongly attracted to one another at intimate contact, slightly overlapping, separation of about 1 femtometer, 10 to the minus 15 meters, via the residual strong force. This allows nuclei with multiple protons and neutrons to remain bound and gives the nucleus its size. Here is a representation of the residual strong nuclear potential between a proton and neutron with parallel spins. The horizontal axis is radial distance, separation from one another. The vertical axis is potential energy. The residual strong force is often modeled as repulsive at distances below 1/2 to 0.7 femtometers, which protects the protons and neutrons' size and gives nuclei and also neutron stars their finite densities. However, these models are not definitively proven experimentally. Models without repulsive cores can also produce the finite nuclear density using Heisenberg's uncertainty principle and the Pauli exclusion principle. This is confusing. The attraction of the residual strong force is short range, decreasing to insignificance at 2.5 femtometers. So very little attraction here. The carbon-12 nucleus has a diameter of about 5.5 femtometers. So the attraction of the residual strong force is only between adjacent or nearby nucleons, not spanning the nucleus. So here's the attractive part. Very strong at 1 femtometer. The residual strong force is spin dependent. It is strongly attractive only between nucleons with the same spin direction. So both spin up or both spin down. Two adjacent protons in intimate contact cannot have the same spin direction due to the Pauli exclusion principle. Likewise for two adjacent neutrons. Two protons, a diproton, will not bind. There is no helium-2 nucleus. Two neutrons, a dineutron, will not bind, even though there is no electrical repulsion. The residual strong nuclear force is strong, but it's selective and complicated. However, one proton and one neutron, deuterium or the deuteron nucleus, will remain bound, though not very tightly, and stable. If the deuterium did not bind, then Big Bang nucleosynthesis in the first minutes after the Big Bang would not have produced deuterium or helium, and there would be no nuclear fusion in any stars in our universe. If deuterium would bind but were not stable, only massive stars, much more massive than the Sun, would undergo fusion, would burn brightly and quickly, and then explode. But happily for us, deuterium is stable. Happily for us, two protons plus one neutron, helium-3, will remain bound and stable. This is critical to stellar nuclear fusion in our Sun. And two protons plus two neutrons, helium-4, will remain bound and stable. This is critical to producing the other elements such as carbon and oxygen. The residual strong nuclear force is not a fundamental force. It is not an attraction between quarks mediated by gluons. The residual strong nuclear force is partly explained as a strong attraction between nucleons, protons and neutrons, mediated by exchange of virtual pions, low-mass mesons. A proton and a neutron exchange identity by exchanging a charged virtual pion, either a pi plus or a pi minus, each being spin 0. As we covered previously, energy can be temporarily borrowed from the vacuum for a limited time. This interaction can borrow the 140 million electron volt mass of the pion from the vacuum to create the virtual pion. But that pion must vanish and return the borrowed energy within 2.4 by 10 to the minus 24 seconds. In that interval, the virtual pion can move no more than 7 by 10 to the minus 16 meters, the radius of a proton or neutron, just enough for two nucleons in intimate contact in the nucleus. After this fleeting time and distance, energy is again completely conserved. This exchange of pions and other low-mass mesons is how the neutron in a nucleus is different than a free neutron, and why neutrons in a nucleus can be stable, while free neutrons are unstable. Color force and color charge. This section is optional and standalone. Aside from electrical charge, quarks have a property called color charge. Each matter quark takes one of the colors, blue, red, or green. Each antimatter antiquark takes one of the anticolors, anti-blue, which is yellow, anti-red, which is cyan, or anti-green, which is magenta. Matter baryons are color neutral, also called colorless or white, by the quarks each having one of the colors, blue, red, and green, with all three colors present. Mesons are color neutral by the quark having one of the three colors, in this case green, and the antiquark having that color's anticolor, and anti-green is magenta. All hadrons, baryons, and mesons are color neutral. Here's a representation of a baryon. One of the quarks is blue, one of the quarks is red, one of the quarks is green. Together they constitute white. In an antibaryon, one of the antiquarks is the anti-red color, one is anti-green, one is anti-blue, and together they are white or color neutral. Gluons carry both color and anticolor charge in a different, complicated way. There are 8 types of gluons. Each type is its own antiparticle. In a baryon, the color force works by each pair of quarks continually exchanging their current colors. For example, 2 quarks whose initial colors are blue and green can exchange their colors by the blue quark changing to green and emitting a gluon whose color is blue times anti-green plus green times anti-blue. The original blue quark gave its blue color to this gluon. This gluon is then absorbed by the originally green quark, which changes to blue, taking the blue color from the gluon. After each such color exchange, the baryon continues to be color neutral. Color is confined to the hadron. This is only a simplified representation of a more complicated situation that I have never studied. Using color in this scheme is merely a useful representation of the underlying symmetries and mathematics based on how we humans see a combination of blue, red, and green lights as white. These particles do not actually have these visible colors. These are quantum numbers or quantum states. In addition to providing the attraction between quarks and affecting their confinement within hadrons, the gluons are also attracted to one another due to their color charges. The gluons are also confined within the hadrons, even though they have zero mass and travel at the speed of light. No isolated free gluon has ever been detected. For the photon, zero mass corresponds to an infinite range for electrical attraction and repulsion via the 1/r² Coulomb force law. The photon has no electrical charge, but the zero mass gluons have color charge and are confined within hadrons. Long-range gluon interactions do not exist. The range of the strong nuclear force, the color force, is limited to the size of a hadron. Light and photons. In the late 1600s, Sir Isaac Newton used one prism to separate sunlight into rainbow colors, and then a second prism to recombine the rainbow back into white light. This recombining was considered proof that white light is the sum of the rainbow colors. This is taught a little incorrectly in elementary schools. Newton believed that light consisted of particles because a pencil beam of sunlight would remain straight and not spread out much. His contemporaries Robert Hooke and Christian Huygens believed that light was a wave phenomenon because of diffraction when light hits a sharp edge. A century later, in 1803, Thomas Young published drawings showing that light is a wave phenomenon when a light beam passes through two slits in a barrier. We will examine this further in a bit. At that point, 1803, no one knew what light was a wave of. Galileo knew that the speed of light was much faster than the speed of sound. In Newton's time, the speed of light was measured using astronomy to within a factor of 2 of the modern value. And in 1729, this was improved to within 2% of the modern value. In the early 1800s, scientists could see that light emitted by the sun, when spread out into colors, was missing certain wavelengths due to their being absorbed by the higher, cooler layers of the sun's hot atmosphere. These are the black absorption lines in this spectrograph image. Around 1860, scientists ionized gases, recorded the narrow emission lines they saw, and found that some of the emission lines matched absorption lines from the sunlight. This spectrograph image is the Balmer series of emission lines of the hydrogen atom. Around 1864, James Clerk Maxwell consolidated the known laws of electricity and magnetism into what we now call Maxwell's equations. Maxwell found that his equations had a solution in vacuum, no electrical charges, that we now know of as electromagnetic waves propagating in vacuum. His equations produced a definite speed of propagation, and he found that this speed matched the known value of the speed of light. It was then clear that light is a form of electromagnetic wave, with a high frequency and short wavelength. Until that moment, physicists believed that light was a wave, but did not know what it is a wave of. Now, in 1864, they understood that light is an electromagnetic wave, oscillating electric field and magnetic field. In 1901 and 1905, Planck and Einstein identified that some aspects of light interacting with matter were best explained by light being discrete bundles of energy quanta that we now call photons, whose energy is proportional to the light frequency, which is inversely proportional to light wavelength. Photon energy, E, equals this amount in the numerator divided by the wavelength. A 400 nanometer wavelength violet photon is 3.1 electron volts. A 700 nanometer wavelength red photon is 1.77 electron volts. So everything we see in the visible light, the photons differ by less than a factor of 2 in energy. Electromagnetic radiation and photons are much more than visible light. Photon energies span 27 orders of magnitude, from 10 to the minus 14 electron volt radio waves, through microwaves, infrared, visible light, ultraviolet, and X-rays, up to 10 to the plus 13 electron volt gamma rays. We covered earlier that electrons bound in atoms have definite discrete quantized electron energy levels. To jump or transition from a lower energy level to a higher energy level, the atom must absorb the precise amount of energy from the external environment, typically absorbing a single photon with the right energy, frequency, and wavelength, as shown here. To fall or drop or transition from a higher energy level to a lower energy level, the atom must emit the precise amount of energy to the external environment, typically emitting a single photon with the right energy, frequency, and wavelength, as shown here. The natural lifetime of how long an electron will remain in an excited state before spontaneously falling or de-exciting to an available lower energy state varies from small fractions of a second to hours, but it will always fall eventually. It can also happen that a photon emitted by one atom can stimulate the immediate fall or transition of another atom, and then another atom, and so on. This is called stimulated emission and was predicted by Einstein. Photons are bosons, and they like to bunch up in the same state. Stimulated emission produces high-intensity, coherent light and is the basis for lasers, 1960, as in our CD players, 1982, and DVD players, 1997, and high-speed telecommunications links in the Internet and telephone system. Laser is the acronym for light amplification by stimulated emission of radiation. And here are examples of laser light. We will not cover the photon's spin, its plane polarization, and circular polarization. Two-slit diffraction and interference. Now we will go back to Thomas Young's 1803 experiment that was similar to passing sunlight through two slits in a barrier and observing the pattern on a distant screen. His result was something like the following image. Light consists of waves, and waves can interfere with one another. So we have bands of lots of light and bands of darkness. Let's look at a single color from a laser. This top pattern is the pattern when there's only one slit that the laser beam goes through, and this bottom pattern is when the laser beam is going through a double slit, and the two images look different. Notice all the extra black bands in the bottom image. The light waves passing through the two slits interfere with one another both constructively, adding bright intensity, such as here, and destructively, subtracting zero amplitude, zero intensity, a node, such as here. Due to having different path lengths and phases from the two slits, in addition to the waves from within each slit interfering with one another as they do here. After Maxwell established in 1864 that light is a form of electromagnetic wave, classical physics could completely explain two-slit diffraction for electromagnetic waves using wave interference. But what about Einstein's photons from 1905? What would the experimental result be if we reduce the light intensity enough that only one photon is going through the experiment at a time? An experiment in 1909 greatly reduced the light intensity. With modern quantum optics, it is possible to transmit a single photon at a time. So, does a photon split into two photons at the two splits? Does the interference pattern disappear? Does each photon go through both slits somehow? Concerning wave-particle duality for photons, Einstein wrote, "It seems as though we must sometimes use the one theory and sometimes the other, while at times we may use either. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomenon of light, but together they do." An individual photon could be detected almost anywhere on the detector screen. The hits of prior photons give us no information about where the next photon will hit. If we record all the spots, the pattern matches better and better the classical intensity pattern as more photons hit the screen. The probability for where the photons hit the screen matches the classical intensity pattern. We see this when a large enough ensemble of photons independently hit the screen. Two-slit diffraction experiments and other double-path experiments can also be done with electrons, neutrons, atoms, or molecules, and we get the interference pattern. Here is an image of the double-slit diffraction of electrons, not photons. In this first image, there are 11 electrons that have hit the detector screen, and we don't recognize any pattern on the screen. Here there are 200 electrons, and we still don't recognize any pattern. Here there are 6,000 electrons, and we're starting to see maybe some bunching and some black areas, but we could be wrong. Here are 40,000 electrons, and here are 140,000 electrons. And now we see high intensity, low intensity, high intensity, low intensity, high intensity, low intensity. With the photon being a quantum mechanical particle, interference is due to each photon interfering with itself due to the two slits, not due to a photon interfering with other photons. This is a little hard for us to believe. Does each photon go through both slits somehow? It's wrong to say that an individual particle took both paths or all possible paths. It would be better to say that the quantum mechanical wave function is as if the particle could take any possible path with some probability amplitude, and we don't know which path it did take because we did not measure which path got taken. If we didn't measure some aspect or attribute, such as which slit the particle traversed, then we do not know it. End of story, and we should not guess. The fact that the probability distribution shows interference due to the wave function being a superposition due to the two slits as if a single particle could possibly go through both slits is very confusing for us laypersons, amateurs, to understand and believe because we don't see anything like this in the real macroscopic world that we see and model from the time we are infants. This is different than the entirety of our experience, reason, and logic about solid objects. Though we do see how water waves pass through slits, but all experiments verify this. For more information on quantum mechanics and failures of classical physics that led to quantum mechanics, try my lecture series here at this URL. Here is a representation of an instrument called a Mach-Zehnder Interferometer. The Mach-Zehnder Interferometer has two beam splitters, beam splitter 1 and beam splitter 2, pieces of glass with one face being half silvered. A collimated light source comes in from the lower left, and the beam splitter splits it in exactly two. One half of the beam gets reflected and heads downward, bounces off this mirror and heads back upward to the second beam splitter. The other half got transmitted through the half-silvered face, transmitted through the glass, transmitted in air, bounces off this mirror, and then hits this top face of beam splitter 2. It turns out, if you carefully configure the experiment and the lengths of the paths, the end result of beam splitter 2 is that all of the light recombines and gets detected by this top detector, D0, and no light gets detected by the bottom detector, D1. This can be explained in terms of electromagnetism, electromagnetic waves, and their phases. So it can be explained classically in terms of Maxwell's equations. However, how does this work with Einstein's photons? All of the photons get detected by D0, and no photons get detected by D1. Does each photon split in two and take the top path and the bottom path? What happens is that the quantum mechanics of the experiment is such that the experiment behaves as if there is a wave function for the top path and a wave function for the bottom path, and we don't know which of the top and bottom paths the photon took because we did not measure it. And the quantum mechanical result is the photon interferes with itself to always be detected by detector 0 and never be detected by detector 1. However, if we change the experiment by trying to detect whether the photon took the top path or the bottom path, we inescapably change the result, and now half the photons will be detected in the top detector and half will be detected in the bottom detector, because they no longer interfere, the photons no longer interfere with themselves when we try to determine which path they took. This Mach-Zehnder Interferometer experiment has also been done with neutrons, and they give the same result. If you want to learn more about the Mach-Zehnder Interferometer, you can find my lecture here. Now there is material about the elementary particles in the standard model that we will not cover. We will not cover the following aspects of elementary particles and elementary particle physics. We won't cover what happens in the Large Hadron Collider, the Proton Collider, with 10 to the 13 electron volts per collision. We won't cover quark-gluon plasma and the relativistic heavy ion collider in Brookhaven, New York, called RIC. We won't cover what happens when you try to pull a hadron apart and how new quark-antiquark pairs get created. We won't cover why the observable universe is filled with matter and not antimatter, when it should have started with an equal amount of both, and they should have annihilated and left us with only photons. We won't cover symmetry laws and their violation, CCP, CPT. The weak interaction is the only fundamental interaction that breaks parity symmetry, and similarly the only one to break charge parity symmetry. We won't cover particle handedness, helicity, and chirality, and how this relates to the weak interaction, and we won't cover hypothetical sterile neutrinos. We won't cover whether antimatter decay lifetimes ever differ from matter. We won't cover quantum entangled states of photons. To a particle physicist, a theoretical physicist, particle physicist looks like the following equation. This is one quantity called the Lagrangian, and all these terms are particle physics interactions. I have no idea what this stuff is, but a particle physicist would. Beyond the standard model of elementary particles. Gravitons. The standard model of elementary particles is consistent with quantum mechanics and quantum field theories. Gravitation is extremely well explained by Einstein's theory of general relativity, which is continuous, not quantized. Gravitational waves have been detected by LIGO for several years. If the gravitational field and gravitational waves are quantized, physicists expect that the quantum of the gravitational field, called the graviton, will be a massless uncharged particle with spin 2, called a tensor boson. This has not yet been detected. Such a particle is beyond the standard model of elementary particles. Grand unification theories and supersymmetric particles. The standard model of elementary particles does not unify the strong interaction with the electro-weak interactions, electromagnetism and weak. Theories that attempt to do so are called grand unification theories, or GUTs. Some of the theories propose additional supersymmetric partner particles, called SUSY, or sparticles, to the existing elementary particles. For every standard model fermion, there would be a new high-mass boson. For every standard model boson, there would be a new high-mass fermion. These have not been detected, but some may be within the energy capable of the Large Hadron Collider. These would be beyond the standard model of elementary particles. This is a diagram showing standard model particles and hypothetical supersymmetric sparticles. Quantum gravity and string theory. Theoretical physicists, such as the fictional Dr. Sheldon Cooper of the Big Bang Theory television series, have been working since the 1960s to quantize the gravitational field, to produce a theory of quantum gravity that unifies general relativity with quantum mechanics and the three non-gravitational fundamental interactions. String theory, superstring theory, and M theory seek additionally to explain elementary particles and their masses in a grand unification theory consistent with quantum gravity. Despite 50 to 70 years of theories, no testable predictions have been produced to verify the theories, and testable predictions are the basis for scientific understanding. This is beyond the standard model of elementary particles. Dark matter and axions. When astronomers and astrophysicists add up the mass of stars, gas, and black holes in a galaxy, the mass of this ordinary matter is only about 15% of the mass needed to explain the amount of gravity they believe exists in the galaxy. They call the unknown 85% of the mass cold dark matter, or just dark matter. They don't yet know what makes up dark matter. If dark matter consists of elementary particles, they are uncharged, interact almost not at all with ordinary matter, and are believed not to be neutrinos. Some models propose hypothetical, as yet undetected, axion particles as dark matter. If axions or other dark matter elementary particles exists, They are beyond the standard model of elementary particles. Dark energy. Astrophysicists believe that our observable universe has been expanding for 13.8 billion years since the Big Bang, and the expansion has been accelerating exponentially since about 4 billion years ago. If this accelerated exponential expansion is attributed to an energy called dark energy, such dark energy would presently constitute 70% of the mass energy of our observable universe. Dark energy is beyond the standard model of elementary particles. Problems with the standard model. The fact that neutrinos have mass means the standard model is not completely correct. The standard model does not explain why our universe consists of matter if the Big Bang initially produced equal amounts of matter and antimatter. If protons are not completely stable and have finite lifetimes, even if many orders of magnitude longer than the age of the universe, this would break the standard model and require new physics. The magnetism of the muon is slightly different from the prediction of the standard model. This is being examined at Fermilab's muon G-2 experiments. There are a few other discrepancies and issues. Nevertheless, the standard model is extremely successful in its predictions. Beware articles touting new experimental results beyond the standard model. Very often the titles are misleading clickbait and the actual result may be unverified or only a possibility or even just a hope or a wish. If there is a verified statistically significant result beyond the standard model, it won't require dubious hints. An example is the current muon G-2 experiments. Articles in their headlines suggest that there is strong evidence that the standard model has been broken. If you read the articles, the experimental confidence level is 4 standard deviations, but physicists don't accept data as a discovery until it reaches 5 standard deviations. So wait and see. It might go away or get explained, and yet the article titles are clickbait. Recent hyped clickbait article titles about muon G-2. Muon G-2 experiment hints at mysterious new physics. Physicists confirm that the muon is more magnetic than predicted. Last hope experiment finds evidence for unknown particles. Muon G2 landmark study challenges the rulebook of particle physics. Muon G2 experiment finds strong evidence for new physics. A tiny particle's wobble could upend the known laws of physics. A tiny wobbling muon just shook particle physics to its core. And tantalizing results of 2 experiments defy the physics rulebook. These articles say that the standard model of elementary particles is now broken. How exciting! Or is it? I'm not a physicist, but my take is to not take scientific news article titles on the web or in popular news at face value. Look for cautious statements within the articles. Titles have become increasingly over-optimistic and clickbait in recent years, in my opinion. Let's talk about the muon G-2. If there were no virtual particle pairs spontaneously popping in and out of the vacuum, the magnetic dipole moment of the electron would be exactly 1 Bohr magneton and its g-factor would be exactly 2. It turns out the electron's g-factor is about 1.001160 times 2, and experiments and theoretical calculations of quantum electrodynamics agree to about 15 significant figures. The muon is identical to the electron except for being about 200 times more massive. It turns out that the muon's g-factor is about 1.001166 times 2, slightly higher than for the electron. Why are the g-factors different? The largest contribution is due to virtual electron-positron pairs popping in and out of existence from the vacuum, quantum electrodynamics. The negative electrical charge of the real electron, or muon, causes the virtual particle pair to polarize, separate, with the virtual positron moving slightly toward the real electron, or muon, and the virtual electron moving slightly away from the real electron, or muon. This polarization of the virtual particle pair slightly screens the charge of the real particle, so the universe sees slightly less charge than the naked particle would have. We can never see the naked particle charge. This polarization effect increases the g-factor for the magnetic dipole moment. I presume because the naked charge is higher than the screen charge that the universe sees, and the magnetic dipole moment is due to the real naked charge, but I don't know. This contribution is high because the electron and positron are the lowest mass charged particles. There is also a contribution from virtual muon-antimuon pairs. A smaller contribution is due to virtual quark-antiquark pairs popping in and out of existence from the vacuum, or from virtual hadrons and antihadrons. It turns out this contribution to the magnetic dipole moment and g-factor is higher for the higher mass muon than for the lower mass electron. I don't understand the reason for the difference. Why are Fermilab physicists excited about the g-factor for the muon? They believe there is a statistically significant gap between the experimental and theoretical g-factors for the muon that is not present for the electron. They believe that the theoretical calculation includes the effects of all elementary particles in the standard model. If this proves the case, it could mean that the muon's g-factor needs to include a contribution from new, higher mass virtual particle pairs that are beyond the standard model and have not yet been detected by the Large Hadron Collider. This could be the first, albeit indirect, detection of supersymmetric particles, sparticles, beyond the standard model. If so, this would require changes to particle physics. It would also be the first indirect detection of real particles by their virtual particle pair screening of a real particle. This would be a real achievement for Fermilab, which does not have a particle accelerator with the high energy of the LHC. However, it is also possible that the quantum field theory calculation of the muon's g-factor needs updating relative to the existing standard model particles, such as virtual quark-antiquark pairs. This would still be an achievement for Fermilab, but not as exciting as discovering a new class of elementary particles for which there would be a Nobel Prize. To take into account virtual quark-antiquark particles, theoretical physicists must do calculations with quantum chromodynamics of quarks and gluons, not just quantum electrodynamics of electrons and positrons. It turns out that QCD is very difficult to do calculations with. requiring massive amounts of computer power to do even medium precise calculations. Some physicists believe that the QCD calculation of the muon's G-2 factor needs to be updated for the known quarks and gluons, and then will agree with the experimental value for muon G-2, not leading to discovery of new particles. If you have looked at any of the articles hyping the Fermilab G-2 experimental results, take a look also at the following article that suggests that the theoretical value needs to be updated with new QCD calculations. Wikipedia articles. I read most of a lot of articles, at least 50 articles from Wikipedia to develop this course. In the PDF documentation, I'm giving you the list of these articles in case you want to read more on your own. Some of them are obviously titled, but others are hard to find unless you know they exist, and so this may be a useful list for you. This is the end of the course. Thank you very much for attending. I hope it's been useful to you.